All right. So let's look at this graph here. Okay. We have a local minimum here, a local maximum here, and a local minimum here. Right? We know this. What I want you to think about now is I want you to think about this in terms of concavity. Right? Because this is how the second derivative test is come into play. So let's look here. Right, at our function here, let's see if we can identify the inflection point for this. Right? So if we had an actual function here, right, we would look for where the second derivative is 0, and then check if it changes from positive to negative or negative to positive there. And that would tell us those are inflection points. Right? Again, so it looks very much like how we use the first derivative test to identify local max and min, except we don't have to care what sign it changes from, just that it goes from plus to minus or minus to plus. Right? If the second derivative changes sign, then the concavity changes. But let's see if we can just look at this visually. Right? So here, this is kind of still a upward opening graph, a smile-shaped graph, until maybe around here somewhere. So maybe around there. Right? So over here, it's concave up. Okay? All right? And again, let me label, these are a local minimum. This is a local max. And this one was also a local min. Right? Now over here, right, in this part here, we're definitely kind of concave down, right? This is more of a frown than a smile. Right? And then, somewhere around here, let's say, it sort of looks like it switches. Right? You want to kind of look for the easiest way to imagine where the inflection point is on a graph is imagine drawing some tangent line. Right? At some point, the tangent line to the graph is going to have to cut through the graph. And that's where the inflection. Right, so in the middle here, we look to be concave down. And then over here, we're concave up again. Right? Because we're smiling. So, can you notice any kind of association here between local max and min and concave up and down? Well, if you think about it, a minimum is kind of at the bottom of a valley, but a valley opens upward. So a local minimum, we should always expect to find it somewhere that the function is concave up. That makes sense? Likewise, a local maximum is at the top of a peak. But if you're at a peak, the only way to go is down. So we should expect a local maximum to occur when the function's concave down. Okay. So remember here, with the second derivative, this is positive second derivative. Here is negative second derivative. And here is, again, positive second derivative. So using this reasoning here, we actually get the second derivative test. Okay. So, second derivative test. Okay. What this is here is we're going to suppose f double prime is continuous near C. Okay. If f prime of C equals 0 and f double prime of C positive, then f has a local minimum at x equals c, or we'll just say at c. Right? So this means if you have a critical number, right, and specifically a critical number where the derivative is 0, not the undefined critical number part. So if we have a critical number and the second derivative is positive, then it turns out that has to be a local minimum, right? And that's because it means you have a critical number that's sitting in a valley, right? Likewise, right? If we have a critical number and the second derivative is negative, then f has to have a local maximum. And why is that true? Well, again, here the second derivative being negative says we're sitting in somewhere that's concave down, and these second derivatives equal 0. They're either going to be at a peak or a valley or an inflection point. And well, here we're sitting at the top of a peak if we're going concave down. Okay. Now the book kind of leaves it here. The book leaves it here. I want to add one more part to this. If f double prime of c equals 0, the test fails. Okay. Why does it fail? Well, it's because we could actually have either situation or neither. Right? An extreme example, so example of failure, here would be consider the function f of x equals x to the 4th. Right? If you graph this, you're going to find something like this going on, right? And it absolutely has a local minimum here at x equals 0. But what you're going to find is that f prime of 0 is 0, which is what you want, but f double prime of 0, the second derivative is 12x squared, that's also going to be. So it is possible for this test to fail. And this is what I was meaning here. So when you're using the second derivative test, what this is saying is that all you have to do is find critical numbers and plug them into the derivative, into the second derivative. Sorry. If you have a positive one, you get a local minimum. If you have a negative one, you get a local maximum. But if you plug it in and the second derivative is 0, the test fails. And this is an example of that. So, let's look at the example we did for the first derivative test, just to see sort of how much easier the second derivative test can be. All right? So again, let's look at this function f of x equals 3x to the 4th minus 4x minus 12x squared 5. Right? This is what we used. Right? F prime of x was 12x cubed minus 12x squared minus 24x. Right? And if you remember, we found that the critical numbers of this, in other words, setting this equal to 0, they were -1, 0, and 2. Well, f double prime of x, so we take our second derivative. This is 36x squared minus 24x minus 24. Right? So what we want to do here is say, well, we have our critical number. And again, all we need to know is whether f double prime is positive or negative, but this we can't factor, so it'll be a little harder to do. But what we can do is factor out a 12 if you want. This will be minus 2x minus 2. So here we're going to put sine of f double prime, right? And then here we'll say so the critical numbers were minus 1, 0, 2. So let's just plug this stuff in. All right, so here we have 36 plus 24 minus 24 if we plug in negative 1 to the second derivative. And this is positive. Right? Since that's positive, then we can say that since that's positive, we can say here that this is a local minimum. Right? If we plug in 0, we're going to get 0 minus 24. That's negative. Maybe instead of putting plus and minus, let me put positive, negative. And this one here is then a local maximum because the second derivative is negative. All right, lastly, if we plug in 2, let's see, this is 36 times 4, 104, minus 24 times 4 is 96, minus 24. All right, and again, we don't need to care about the actual number. All we need to know is that's a positive number. And so since the second derivative is positive, this has to be a local minimum. Right, so the second derivative test allows us to classify these a lot more easily, right? Because we don't have to test numbers on either side of the critical numbers. We just have to plug the critical number into the second derivative. However, I want you to remember here that if you plug it in and you get 0, there's some issues, right? It no longer works. All right. So with that in mind, we'll end here and for the next stuff.